Hi and welcome to this video on the binomial theorem. So in this video we're going to look at using the binomial theorem to expand brackets containing two terms. So binomial theorem is specifically for expansion of brackets containing two terms, which is where the word or the phrase binomial, bi meaning two, comes from. So this binomial theorem is given to you on page 20 of your formula and tables book. So this is an alternative method than using Pascal's triangle. So using Pascal's triangle and this binomial expansion given in your log tables will give you exactly the same answers. However, it's a lot easier to work with the harder questions using the binomial theorem rather than Pascal's triangle. So what I would say is Pascal's triangle is good to look at, but really the binomial theorem will be that bit more important. So at the very end of page 20, we have this piece here, which is about the binomial theorem. We have x plus y to the power of n is equal to the sum, beginning as or equal to 0 all the way up to n, of n, choose or, x to the power of n minus or, y to the power of or, and it gives the full expansion here. It also gives us the binomial coefficients. So you may have already seen this n choose or as you were dealing with combinations at the start of probability. So we're going to use this page a lot, so if you have your log tables handy, do keep them open for the duration of the video. So what we're going to cover in today's video, we're going to look at calculating and working with the binomial coefficient, so that idea of choosing. We're going to use the binomial theorem to expand a bracket, and we're going to use the binomial theorem to find specific terms of an expansion. So that is the most common that we've seen, but we have only seen it on mock and sample papers. This has never been asked, so just bear that in mind. So let's take a look at our first example. We're talking about combinations and the binomial coefficient. So this is kind of tying into combinations, but it is the binomial coefficient, so I'm going to cover it here. So without using your calculator, show that 5 choose 3 is equal to 5 choose 2. So I'm going to go straight to page 20 of my log tables, and I can see at the very bottom of this, it tells me that n choose or is equal to n factorial over or factorial times n minus or factorial. Okay, so I'm going to just write this up so you guys know what I'm using. Is equal to n factorial all over or factorial n minus or factorial. So if we calculate, and they have specifically told us not to, but if you did into your calculator 5 choose 3, you will find that the both answers, well, that answer is 10 and 5 choose 2 is 10, but we want to show it using this formula. So 5 choose 3 is going to be n, which is 5 factorial, all over or factorial, which is 3 factorial, and 5 minus 3, which is 2 factorial. And is that equal to 5 choose 2, which is 5 factorial, over or factorial, which is 2 factorial, n minus or, which is 5 minus 2, 3 factorial. And that is true. And the reason it's true is because 3 factorial, 2 factorial, so I'm just going to go underneath it, that's 3 by 2 by 1, and 2 factorial is 2 by 1, while this is 2 by 1 by 3 by 2 by 1. And we're multiplying exactly the same thing, and since the order does not matter when we multiply, this is true. Okay, so as we're working with this, we can clearly see that this is true no matter what. Now, if you want to work out 5 choose 3, we have a button on our calculator, so I'll just show you that really quickly. So the calculator, I'm just going to show you the Casio really quickly. So the NCOR, I know it's a bit blurry here, but if you have your Casio in front of you, take a look. It's shift and then NCOR. So for example, if I wanted to put 5 choose 3 into the calculator, I type 5, then I click shift, then I click the divide button. So NCOR is in yellow above the divide button, which is why we need the shift, and then I press 3 equals, and you should get 10. Okay, so just a little bit of practice on this, and it will lead a bit more to the example. What I would say is let's work through all of it. So if I wanted to work, and I'm just going to change color now for a second because this is nothing got to do with the example that I'm doing here. If we worked it through, we start with 5 choose 0, we have 5 choose 1, We have 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. Okay. I can't choose a negative number, because if I have 5 things, I can't choose negative one of them. So the smallest I could do is if I have 5 things and I don't choose any, so I choose 0. The biggest number I could choose is 5. Okay, so there is 6 things that I could do if I have 5 objects. So I have 5 choose 0, 5 choose 1, 5 choose 2, and so on. So if you put those into your calculator one by one, what you'll notice is this. 5 choose 0, I get 1. 5 choose 1, I get 5. 5 choose 2, I get 10. 5 choose 3, I get 10. 5 choose 4, I get 4. Sorry, 5 choose 4, I get 5. And 5 choose 5, I get 1. And hopefully what you're seeing now is there's kind of a symmetrical property here. So we have this idea. These two mirror each other. These two mirror each other. And finally, these two mirror each other. The question is, well, why? What is it? What is the rule about the mirroring? And if you take a look at our OR, so remember that they're all n choose OR. Take a look at this number and this number. They are adding to 5. So when my ORs add to 5, they'll be symmetrical. So for example, 1 plus 4 gives me the top number, which is 5, so they'll be symmetrical. And 2 plus 3 gives me 5, so they'll be symmetrical. Now, it is something, as we work with the binomial expansion, you're going to see and you're going to recognize more and more, but it's important as we move to the next example that you have this idea of the symmetrical property. So, if 15 choose OR plus 3 is equal to 15 choose 4 OR minus 13, find OR given that OR plus 3 does not equal 4 OR minus 13. Okay, so two things could be true. The bottom lines could be the same. So 15 choose 2 is equal to 15 choose 2. So those two bottom lines could be the same. Now, they've specifically told us here that they are not. They've told us that the bottom line, so that bottom line does not equal the other bottom line. Okay, so that's for sure. The only other thing that could make them equal is if that symmetrical property exists. So basically, whatever those denominator, well, not the denominator, but whatever those ORs are, they add to give me 15. So I know that OR plus 3, when added together with 4 OR minus 13, they should add up to my n, which in this case is 15. So adding those together, I get 5 OR minus 10 equals 15. 5 OR is equal to 25. So OR is equal to 5. So a super simple little question, but really could have stumped you if you didn't have that idea in your head about how each of those terms relate to each other and the idea of the symmetrical property. So do bear that in mind. So now let's look at a binomial expansion question. So there's two parts to this. Expand P plus Q to the power of 5 by the binomial theorem, and use the expansion to evaluate the third term when P is equal to 0.6 and Q is equal to 0.4. So first thing I'm going to do, I'm going to go to page 20 and pull that out. Now, when I'm using the binomial theorem here in the log tables, what I get is 2 equals, and we generally say 1 equals per line. So this thing here, without the sum, is the general term. Okay, and I'll talk about this a bit more in the next example. This is my general term, and you see that actually it appears here as well. Okay, so that's my general term there as well. But I'm going to use the main part of it, so not the general term. I'm going to use the main part of it here to help me expand. So it is x plus y to the power of n. So the first thing I'll notice here, my n is 5. Okay, the x is p and the y is q. So what I get is 5 choose 0, x, so my first part or my first term in the bracket, p to the power of n, which is 5, plus n choose 1, so 5 choose 1, and then I get p to the power of n minus 1, which is 4, and q to the power of or, which is 1. Okay. So plus 5 choose 2, and I get p to the power of 3, q to the power of 2, plus 5 choose 3, p to the power of 2, q to the power of 3, 5 choose 4, nearly there, p, q to the power of 4, plus 5 choose 5, and I'm looking at this last term here, and it's q to the power of 5. Now, let's take a look at some interesting things that happen. So when I have a power of 5, and I expand my bracket, I'll get 6 terms. So think about it from what we already know. When I square a bracket that has 2 terms, I will get 3. Think of that. So if you did x plus y and you squared it, you would get 3 terms. So you always get an extra term. As we use the binomial theorem, hopefully you can see why. No matter what that power is, we actually start at 0. And that's what gives us that extra term in our answer. The second interesting thing to note is the powers. So the first one has a power of 5. The second one, there's 2 pieces. One is a power of 4, one is a power of 1. The third piece, power of 3, power of 2. So your powers should constantly add to your n, which in our case is 5. And they will. And it's something you can check as you work along. So now let's work with our 5 choose 0. So I know 5 choose 0 is 1, so I get 1p to the power of 5 plus 5 choose 1, 5p to the power of 4 q plus 5 choose 2 is 10, p to the power of 3, q to the power of 2 plus 5 choose 3 is 10, p squared, q to the power of 3 plus 5, p, q to the power of 4 plus 5 choose 5 is 1, q to the power of 5. And we have our answer there. So again, hopefully you can see that symmetry happening as we expand out this bracket. This question has a follow-on one that says use the expansion to evaluate the third term when p is equal to 0.6 and q is equal to 0.5. So let's figure out our third term. So this is my first term, 5 choose 0, 5 choose 1 is my second term, and here is my third term. Now, it's interesting to note, and we'll need this for the follow-on example, in my third term, the OR is actually 2, because we start at 0. So my first term is OR is equal to 0. My second term, OR is equal to 1, and so on. So I'm going to take this term, which is 10, p to the power of 3, q to the power of 2, and they've told me p is 0.6, power of 3, and q is 0.4 squared. Okay, so let's multiply that out. So we should get 216 over 625. But since they give it in decimal, I would answer in decimal, and we get 0.3456. Now, this may or may not look familiar to you, depending on where you're at. But if it does look somewhat familiar, the reason is that this has just led us to basically use Bernoulli trials, which is known as the binomial distribution, which is a way of calculating probability. So basically they've given us a probability of 0.6 and the probability of it not happening is 0.4, and they've worked it through. So this is kind of the background to where Bernoulli comes from. So if you haven't already seen it, be aware as you move into it. If you've already seen it, make sure you can make that connection. So let's look at another binomial expansion question. Find the first 3 terms of this expansion. So I have 1 plus x to the power of 9. Now, what I would say in this case, it's so important to be very clear on what you're doing, especially here, because in our log tables, it gives us x plus y. Here we have 1 plus x. So the y is now the x is now a 1. So it's very easy to become confused. So what can be useful is if you talk about them as the first term and the second term within the bracket. So for example, I'm going to first make a note of n. So n in this case is 9. I only want the first 3 terms, which is great because it's a power of 9, if I wanted all the terms, I would have had 10 terms. So first thing I do is I do 9 choose 0. I have my first term to the power of 9. And my first term is 1. So I'm not talking about my x to the power of 9, because then you'll do it wrong. Okay, so just be so careful. The next one, 9 choose 1. 1 to the power of 8, x to the power of 1, or just as is. Next, I do 9 choose 2. 1 to the power of 7, x to the power of 2. So my first term to the power of 7, my second term to the power of 2. So what I need to do, I need to clean this up. I'm going to do 9 choose 0. I put that in my calculator. I get 1 times 1 to the power of 9. So this is just going to give me 1. I then do 9 choose 1, which is 9 times 1 to the power of 8, which is 1. So that gives me plus 9x. Then I do 9 choose 2 into the calculator. We get 36 times 1 to the power of 7, which is 1, so 36x squared. So they are the first 3 terms in that extension. So it will go da 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 on, but they're the first 3. So this question also has a second part where it says hence. Okay, so based on what we've just done, so they don't want me to start again, they want me to use what I've just done. It says hence, deduce the first 3 terms of this expansion. Okay, so I still have a bracket, I have a 1, I have a power of 9, but what's different is this piece here. Okay, so in my old one I had a plus 9, here I have a minus x over 3. So effectively what's happened is my x in my previous one has been replaced by a minus x over 3. And it's really important when we're doing binomial that the signs are used as well as whatever the term itself is. So what I'm going to do is everywhere I have an x in my first answer, I'm going to sub in a minus x over 3 to get my second answer. So I get 1, which won't change because it is what it is, plus 9. Now, instead of having x, what I'm going to have is, and I'll do it in a slightly different colour so we can see, minus x over 3. So I've subbed in. Okay, then I have plus 36, and again, instead of x, I'm subbing in minus x over 3, and it's squared. And again, this is only my first 3, so it does go on. So I have a little bit of cleanup to do, and I get 1, no cleanup required. Here, I have a plus by a minus, so I'm going to end up with a minus. My 3 divides into my 9 3 times, so I get a minus 3x. Now what I have here is I have minus x over 3 squared. So I'm going to do this in 2 parts. I'm going to leave my 3 where it is, and I'm going to square it. Now, when I want to square a fraction, I square the top and I square the bottom. Although the fraction is negative, when I square any negative number, it will become positive. So I get x squared over 9. Sorry, that should be a 36. So I get x squared over 9, and I still have a little bit of cleanup to do there. So I go 1 minus 3x. 9 divides into 36 4 times, so I get plus 4x squared plus dot dot dot. So that's how I could deduce it. Now, usually, and this is a sample paper, so bear that in mind, usually if this was asked with a hence, or any question is asked a hence, they say hence or otherwise. So you could, if you'd wanted, to go straight back to the binomial theorem as given on page 20 and to use that to calculate or to figure out those first 3 terms. But this deduce was a nice, quicker way to work with it since we'd already done kind of the hard work. Okay, so now that hopefully we understand how to expand using the binomial theorem, we're going to move a step further and we're going to look for a specific term using this theorem. So find the fourth term in the expansion of x squared minus 2 over x to the power of 9. So I've just pulled up the binomial theorem from page 20. So we're going to look at what I've talked about a little bit earlier, which is the general term. So you can pull the general term from one of two places. I find students find it easy to spot it here. They're not confused, but this is exactly the same as what we have here, just ignoring the summation, that capital sigma in front, okay? So that's the general term. So we're going to use that when we're looking for a specific term, okay? So just to remind you, this thing here, general term. And the general term means basically a formula that can be used to get any term. So in this case, I want the fourth term. So the first thing I need to identify are my letters. So I know I have n equals 9. That's okay. We can pull that out. That's my power. The second thing I want to identify is my OR. It's the bottom. So it's n choose OR. So my fourth term, bearing in mind that my first term starts at n choose 0, second n choose 1, this is going to be n choose 3. So fourth term, we know that means OR equals 3. So now my general term is n choose OR, x to the power of n minus OR, y to the power of OR. So I have 9 choose 3. X is my first term in my bracket, which in this case is my x squared. So I have x squared, and it's n minus OR. So 9 minus 3, so it's power 6. Now my second term, and I'm going to just highlight this, it's this whole piece here, including the sign. So that's really important. So minus 2 over x to the power of OR, which is 3. So that's using my general term to get the fourth term. Now, you can't leave it like this. You will need to tidy it up. So the first thing we can do is do n choose 3, NC3 on the calculator, and we get 84. Using our laws of indices, x squared all to the power of 6, we multiply out that, we multiply the two powers and we get x to the power of 12. And we then have minus 2 over x to the power of 3. So, remembering how this works, we do the top to the power and the bottom to the power. So we should be able to tidy this up a bit more. We should be able to see that x cubed goes into this. So remember, laws of indices, we're going to subtract. So this would leave me with 9. Okay, so we get 84 x to the power of 9, and we do minus 2 to the power of 3, which will give us minus 8. And we should be able to multiply that out, and we get minus 672 x to the power of 9. So the fourth term in the expansion is minus 672 x to the power of 9. So the next example is again looking for a specific term. However, they don't tell us which term it is. So it asks us to find the coefficient of x to the power of 5 in the expansion of 2x squared plus 1 over x all to the power of 7. Now, the complication here is because both the first and second term within the bracket contain x's, and not just an x. There's an x squared and 1 over x. So these are going to have to work in some kind of combination. So my problem at this point is I don't know exactly which term I want, therefore I don't know which OR I need. So what we're going to do is we are going to use our general term again, and we're going to use that to help us figure out first which term has an x to the power of 5, and from there we're then going to work out what is its coefficient. So looking at page 20, I'm going to go again to look for the general term. So my general term is n choose or, x to the power of n minus or, y to the power of or, and we know in this case n is 7. So I'm going to fill in as much as I can. So I know I've 7. I don't know what my or is in this case. The x represents the first term in my brackets. That's a 2x squared to the power of n minus or. So that's 7 minus or. And y represents the second term. So that's 1 over x. And it's to the power of or. Okay. So that's as far as I can go with my general term. However, what I do know is all the x's, I want to get that to be x to the power of 5. So I'm going to pull out, and I'm going to use, again, my highlighter here. So I'm going to take my x to that power and my 1 over x to the power. Now, notice I'm ignoring the 2. And I'll ignore any coefficient there, and I'd even ignore any negatives. Because all I know is there's going to be an x to the power of 5. I don't know anything about its coefficient. I don't know anything about its sign. So I simply ignore it. So what I get here, okay, so I'm just going to take my x's and I'm going to just change color so we can see a difference in what we're doing. So we're going to have an x squared to the power of 7 minus or, and I have a 1 over x to the power of or, and that should all give me, for the or I want, x to the power of 5. So we're going to use a lot of our laws of indices here. So I get x to the power of 14 minus 2 or. 1 over x is basically x to the power of minus 1. So I get x to the power of minus 1 to the power of or. That's all x to the power of 5. Moving up here, I get x to the power of 14 minus 2 or times x to the power of minus or equals x to the power of 5. Combining these, I use law 1, which is adding. So x to the power of 14 minus 2 or minus or equals x to the power of 5. So I get x to the power of 14 minus 3 or is equal to x to the power of 5. At this point, because I've got my bases equal, I can ignore my bases. I get 14 minus 3 or is equal to 5. Minus 3 or is 5 minus 14 minus 9 or is equal to 3. So that's a really important answer, because what I figured out now is I want the fourth term, so when or is equal to 3. So I can go back to my general term now. So I'll go back to my general term and I'm going to sub in when or is equal to 3. So I've got 7 choose 3, 2x squared to the power of 7 minus 3, so that's 4, 1 over x to the power of 3. And I'm going to do a little bit of work on that. So 7 choose 3, 35, 2x squared to the power of 4. So that's 2 to the power of 4. So 2 to the power of 4 is 16. X squared to the power of 4, you're multiplying, that's x to the power of 8. And it gives me 1 over x to the power of 3, because 1 to the power of 3 is still 1. So we've 35 by 16, which gives me 560. And working with x to the power of 8 divided by x to the power of 3, that gives me x to the power of 5. So my coefficient is 560. So I'll remember I was looking for the coefficient of my x to the power of 5 term, which is what I've got, and that coefficient is 560. So our last example now is looking for a specific term again, but unlike the last one where it said x to the power of 5, they've asked us to find the coefficient of the term independent of x. Okay, so what that means is it's the constant. Okay, so what we're looking for here, it's the constant, no x, but what we're going to deal with it is x to the power of 0. Because we know, hopefully, that x to the power of 0 is 1. Anything to the power of 0 is 1. So basically the constant term technically has an x, but it's an x to the power of 0. So we're going to work this exactly like our last example, but letting the x's come to x to the power of 0. Okay, so first thing I'm going to do, I'm going to get page 20 and I'm going to take my general formula. So I'm dealing with n equals 8. My general formula is n choose or x to the power of n minus or y to the power of or. So I get 8 choose or. X is my first term, which in this case is x. 8 minus or. Y is my second term, so it's 1 over x to the power of or. Just like before, I'm only going to take my x's. No signs, no numbers. And I'm going to just take them for a second. And I'm going to work in a different color. So you have x to the power of 8 minus or. 1 over x to the power of or, and I want that to be equal to x to the power of 0, because just to remind you, the term independent of x has no x, so x to the power of 0 will show as 1. We'd never leave it as x to the power of 0. So working this through, I get x to the power of 8 minus or. 1 over x is x to the power of minus 1, so that gives me x to the power of minus or. This equals x to the power of 0. So I'll just move up here. X to the power 8 minus or is equal to x to the power of 0. X to the power 8 minus 2 or equals x to the power of 0. So now I've got both the same base. I can ignore my bases and deal simply with my powers. And I get 2 or equals 8. Or equals 4. So again, or equals 4, that means it's my fifth term. And I'm going to go back to my general term again, and I'm going to sub in 4. So I have 8 choose 4, x to the power of 8 minus or, so that's 4, 1 over x to the power of 4. Okay, so 8 choose 4 is 70, and basically x to the power of 4, and it's times 1 over x to the power of 4. They will cancel each other out, so that simply equals 70. So the coefficient of the term independent of x, so i.e. the constant in this expansion, is 70. So this would be a very good time for you to add on your revision of the binomial theorem. For Bernoulli, to add on the binomial distribution, so into Bernoulli. So what I'll do is I'll link the video here. This is all the basis for working through that, and hopefully Bernoulli will make a lot more sense having gone through this video.